Chapter 2.3, Part 2, Conservation of Linear Momentum. Previously we learned about momentum, we learned the definition of momentum, and in 2.3 Part 1 is where we were introduced to momentum in this IAL lessons. By the end of this section, you should be able to explain the principle of conservation of linear momentum. Make calculations based on the conservation of linear momentum. Okay, so I'll go to the definition, and here is what we call a Newton's cradle. What happens is when you release this, it will go like that and hit this, and as soon as it hits this, the momentum will be transferred, so this will move up. So assuming there is negligible friction or no friction, the momentum of this ball, so what will happen is this will come over here. As soon as it hits this, it will stop, and at that instant this ball here goes up. All of these three balls and the ball that came in contact here will be stationary, but this will move with the same velocity that with which it hit this. Okay, so what happens is here in the beginning, the momentum of this is 0. The momentum of this has some certain momentum. What happens is the total momentum then will be the momentum here 0 plus the momentum of this. Now after collision, what happens is this will become stationary, so will be the three balls here, but this will be moving, and according to the law of conservation of momentum, you would have learned it in the other classes also, the total momentum before is collision is equal to total momentum after collision in a closed system, or provided there is no external force acting. So that's why after this collides, this has to move with the same speed as this, because these and these three here stop after this collides, and then this will be moving. So the momentum of these four, this and after the collision is 0, and the momentum of this will be the total momentum. So that total momentum, which is the momentum of this, should be equal to the momentum of this. So that's why this will move with the same speed as the speed with which this hit this ball here. Okay, so linear momentum, because linear means it's moving in a straight line. Now there is also rotational momentum, which is not in this lesson. Okay, so to help you all understand this better, let's go through this example. In an American football match, now there is a picture actually. So here, this is American football. The stationary quarterback is tackled by a defender. So they are the players, who dives through the air at 4 meters per second, and in mid-air grabs the quarterback, and the two fly backwards together, ignoring any friction effects. Calculate how fast the two will come back if the tackler has a mass of 140 kilograms and the stationary player has a mass of 95 kilograms. Now again, when it comes to a question like this, it's better if you can sketch a diagram. In an American football match, the stationary quarterback, so I will label that as Q. The quarterback, I will call him Q. Okay, that's better. Okay, so he is stationary. So again, before collision, I'll just write before, and before what happens is one is stationary. So here this is Q, quarterback, U is equal to 0, not moving. Tackled by a defender who dives through the air at 4 meters per second, and in mid-air grabs the quarterback, and the two fly backwards together. Okay, so let's call this person D, is moving that way. Four meters per second, and in mid, so 4 meters per second. So this person is coming from one side, like they fall backwards. Grabs the quarterback and the two fall backwards together. Ignoring any frictional effects, calculate how fast the two will fly back if the tackler has a mass of 140 kilograms and the stay. So this person has a mass of 140, 95 and 140. So let's label those two also. 95, 140. Okay. Now it's easier. Now after they collide, they move together. So we can even draw that one. So it's an inelastic collision. So after collision, let's say they move in this direction. They have to move because in the beginning the momentum is this way. So this momentum is 0. So total momentum before is actually 140 times 4. That should be the same momentum here. So they have to be moving to the right. Now the total mass here is 95 plus 140, which is 235 kilograms, the total mass, because they move together. And let's call this V. Now most probably they will ask us to find this. Okay, again, if you read the question, you can see that. Consider the entire situation to be happening horizontally. How fast the two will fly back if the tackler, yeah, so that's why you're supposed to find V. Now you see it becomes a lot easier once you draw the diagram. So both are moving together, so that's why I drew it as one particle. Quarterback stationary, so 0 momentum. The momentum of this Q, quarterback, is 0 because it's not moving. The equation for momentum is equal to mass times the velocity. So the momentum of the defender is the total momentum before collision, which is 140 times 4. That is 560 kilogram meters per second. Now in this case, you can see according to this diagram, it is to the right. So after collision, according to the principle of conservation of momentum, which states that the total momentum before collision should be equal to the total momentum after collision in a closed system, or if there is no external resultant force acting. Now that's what we are finding. So the total momentum after collision should be also equal to 540 kilogram meters per second. And here they write both because they both move as one body. They coalesce or they stick together. In other words, they fly back together. Yeah. So we are using this again. Now the total, we are making V the subject of the equation. So the total momentum is now 560 and the total mass is 235. Then you get 2.4 meters per second. In a collision in which two objects join together to become one and move off together, they are often said to coalesce. That's what I mentioned. So we use different words. Stick together, coalesce, couple, move together, all mean the same thing. Okay, so here is an explosion. This is a flying trapeze. Explosion is when the total momentum is 0. Now you can see they are like this. They are holding each other. So we can say at this position they come to a momentary stop. They come to a momentary stop. So the total momentum in this at this point is 0. Now what happens is one releases the other. Then what happens? They move apart. So the total momentum is 0 in the beginning and they move apart. The two bodies, if two or more bodies move apart when the total momentum in the beginning is 0, that is called an explosion. So in this case what happens is when they release their hands, one of them will move to the left, the other one will move to the right. they are moving away from each other, and in the beginning the total momentum was 0. This is what we call an explosion. Now in a real explosion, in the normal life, we say, so in the normally when we use the word explosion, what happens is, if the case of something that explodes, everything is stationary and then the pieces fly apart from each other. Okay, they have to move in different directions, because in explosion all of them can't move in the same direction, because the law of conservation of momentum now, which states that the total momentum before should be equal to total momentum after. Now in explosion everything is stationary in the beginning, so that means the total momentum after the explosion, after that interaction, should also be 0. So they have to move in different directions, they can't move in the same direction. If they move in the same direction, then the total momentum then may not be 0, so they can't be 0. They have to move in different directions so that the total momentum is 0. Okay, let's go through an example for consolidation. If the boy has a mass of 55 kilograms, steps forward at a speed of 1.5 meters per second, what will happen to the board which has a mass of 36 kilograms? Ignore frictional effects. Now maybe you would have tried this. You might think, if it is your first time walking on a boat, something like this, where you are getting into a boat or getting off a boat, it's not like the normal flow. So when you move forwards like this, the boat will move backwards, because the boat is not fixed to the ground like this part here. So what will happen is, when you move to the left, the boat will move to the right. The boat will gain an equal momentum to the right as you gained momentum to the left. So this situation, now this is also an explosion, because in the beginning the boat and the boy was stationary, and then what happens? They move apart. This situation is an explosion. So total momentum before is equal to total momentum after, which is equal to 0. That means the momentum of the boat plus the momentum of the boy should be equal to 0 before and after. So we can say the momentum of the boat is equal to minus the momentum of the boy, because the boat gains the same amount of momentum to the right as the boy gains that same amount of momentum to the left. So when the two are added up, the total momentum is still 0. Now we can calculate the momentum of the boat, which is the same as the momentum of the boy but in the opposite direction. So momentum of the boat is equal to minus the momentum of the boy, which is this one. The mass of the boy is 55 and the boy is moving to the left. So they have taken to the right as positive. That's why this is a negative sign here, times 1.5. The minus sign is taken out and written here. So the momentum of the boat will be 82.5 kilogram meters per second to the left. Now we are supposed to find the mass of the boat. The speed of the boat, because they are already given the mass. They are asking what will happen. So the boat will move to the right, and we can also mention with what speed it will move to the right. Then we can use this equation: momentum of the boat times the velocity of the mass of the boat times the velocity of the boat will give you the momentum of the boat. And they have taken to the left as positive. That's why to the right it's negative. Now the momentum of the boat is to the right. They get a negative sign, means they have taken to the left as positive. So left positive means whatever is to the right is negative. So what they have done is they have taken to the left as positive. Alright, then we can use this. The mass of the boat is 36 kilograms. Then we get minus 2.3 meters per second. So the boat moves at 2.3 meters per second in the opposite direction to the boy. Okay, investigation transfer of momentum. So in the physics lab we can do experiments like this with trolleys and find the change in momentum, or we can verify the principle or law of conservation of momentum, actually, which is this equation here. So what is happening here is there is a magnet, slotted mass, and let's see, so they can use magnets also. if you have two like poles facing each other, and let's say if there was a string or something connecting them, and once you cut that string, because the like poles repel each other, the trolleys will move apart. So that is also an explosion, because in the beginning the trolleys were stationary and then they move apart because of the repulsion, and when the thread or something that is connecting the two trolleys is cut. Okay, so here it's like a spring mass system, so there is something that pushes this. You can investigate the transfer of momentum in collisions in the school lab using trolleys or sliders on an air track. So there is a video on the website, or you can even check online. There are so many videos of how to use the air track. When it's an air track, the objects, or in this case if it was something like a trolley, it will be floating. So there is no friction between the ground and the trolley, because the trolley or that whatever object will be on a cushion of air. It will be above the ground, above the whatever it's supposed. So there is no contact with the table or the air tract. By recording the movement of one trolley crashing into another, you can find the momentum of each trolley before and after collision. The calculation of summing the total momenta, plural of momentum is momenta, before and after collision will allow you to verify the principle of conservation of linear momentum. Try different types of collision and trolleys with different masses. You could also try an explosion in which trolleys spring apart from a stationary position. So we can use a light gate or a motion sensor to find the speeds or velocities of the trolleys after the explosion. So what we can do is we can measure the mass of the trolley using a top pan balance. We can measure the speeds of the trolleys using a light gate connected to a timer or motion sensor, and then we can find the individual momenta and check that the total momentum before, which is 0, should be equal to total momentum after. See, in which you can also try an explosion in which the trolleys spring apart from a stationary position. In experiments using trolleys, we often find that the momentum is actually not conserved in the measurements we make, because there is friction between the ground and the trolley. With air track collisions, the measurements match very closely or exactly with the conservation of momentum theory, because there is no friction between the trolley and the table or on the ground, because it will be floating. What might be the reasons for this difference between the two types of experiments? Okay. Then again, these Newton's laws I have explained in detail in a separate video, and this is the final one, the principle or law of conservation of linear momentum. Means the vector sum of momenta of all objects in a system is the same before and after any interaction or collision between the objects. And by the way, it's also important to mention in a closed system, or provided there is no external resultant force. An explosion is a situation in which a stationary object or system of objects, joined objects, separates into component parts which move at different velocities. Momentum must be conserved in explosion. So in the explosion, the total momentum before the explosion has to be 0, and it will be equal to the total momentum after explosion, which is also 0 because of the principle or law of conservation of momentum. Okay, so that's the end of that, and you can answer all those questions. There were some questions throughout the chapter. You can answer all those questions, and you can also answer all the end of chapter questions. So make sure you answer all the questions here and check the answers. The answers are in a separate document, and do all the questions there, and if there are any questions here, you can do all of them also. Yeah, these questions. So make sure you answer all these questions and check your answers. Then after doing that, you can start doing the end of chapter questions, the exam style questions, these questions. Okay, so here is the Newton's cradle. I explain to you how it works. Yeah, so that's the end of chapter 2.